Today is 24th March, and I am reading from Using SQLite by J.A. Krebich. And today I'm continuing my reading from chapter 4, uh, which is the SQL language. And today's section is SQL Data Languages. SQL commands are divided into four major categories or languages. Each language defines a subset of commands that serve a related purpose. The first language is the Data Definition Language or DDL, which refers to commands that define the structure of tables, views, indexes, and other data containers and objects within the database. Create table used to define a new table, and drop view used to delete a view are examples of DDL commands. The second category of commands is known as data manipulation language or DML. These are all of the commands that are insert, update, delete, and query actual data values from the data structures defined by the DDL. Insert used to insert new values into a table, and select used to query or look up data from tables are examples of DML commands. Related to the DML and DDL is the transaction control language or TCL. TCL commands can be used to control transactions of DML, and DDL commands used to begin a multi-statement transaction, and commit used to end and accept transaction are examples of TCL commands. The last category is the data control language or DCL. The main purpose of the DCL is to grant or revoke access control. Much like file permissions, DCL commands are used to allow or deny specific database users or group of users permission to utilize or access specific resources within a database. The permissions can apply to both the DDL and the DML. DDL permissions might include the ability to create a real or temporary table, while DML permissions might include the ability to read, update, or delete the records of a specific table. Grant, used to assign a permission, and revoke, used to delete an existing permission, are the primary DCL commands. SQLite supports the majority of standardized DDL, DML, and TCL commands, but lacks any DCL commands. Because SQLite doesn't have user names or logins, it does not have any concept of assigned permissions. Rather, SQLite depends on data type permissions to define who can open and access a database. Data definition language. The DDL is used to define the structure of data containers and objects within the database. The most common of these containers and objects are tables, indexes, and views. As you will see, most objects are defined with a variation of the create command, such as create table or create view. The drop command is used to delete an existing object and all of the data it might contain. Examples include drop table or drop index. Because the command syntax is so different, statements like create table or create index are usually considered to be separate commands, not variations of a single create command. In a sense, DDL commands are similar to C++ header files. DDL commands are used to define the structure, names, and types of the data containers within a database, just as a header file typically defines type definitions, structures, classes, and other data structures. DDL commands are typically used to set up and configure a brand new database before data is entered. DDL commands are often held in a script file so that the structure of the database can be easily recreated. Sometimes, especially during development, you may need to recreate only part of the database. To help support this, most create commands in SQLite have an optional if not exists clause. Normally, a create statement will return an error if an object with the requested name already exists. If the optional if not exist clause is present, then the error is suppressed and nothing is done, even if the structure of the existing object and the new object are not compatible. Similarly, most drop statements allow an optional if exists clause that silently ignores any request to delete an object that isn't there. In the examples that follow, the if exist and if not exist command variations are not explicitly called out. Please see the SQLite command reference in Appendix C for full details of the complete syntax supported by SQLite. Tables. The most common DDL command is create table. No data values can be stored in a database until a table is defined to hold that data. At the bare minimum, the create table command defines the table name, plus the name of each column. Most of the time, you will want to define a type for each column as well. Although types are optional when using SQLite, optional constraints, conditions, and default values can also be assigned to each column. Table level constraints can also be assigned if they involve multiple columns. If some large RDBMS systems, create table can be quite complex, defining all kinds of storage options and configurations. SQLite's versions of create table is somewhat simpler, but there are a still great many options available. For full explanation of the command, see create table in Appendix C. The basics. The most basic syntax for create table looks something like this. Create table, table name, and column type. A table name must be provided to identify the new table. After that, there is just a simple list of column names and their types. Table names come from a global namespace of all identifiers, including the names of tables, views, and indexes. Clear and concise identifier names are important. Like the database design itself, some careful thought should be put into the table name, trying to pin down the precise meaning of the data it contains. Much the same could be said of the column names. Table names and column names tend to be referenced frequently in queries, so there is some desire to keep them as brief as possible while still keeping their purpose clear. Column types. Most databases use strong static column typing. This means that the elements of a column can only hold values compatible with the column's defined type. SQLite utilizes a dynamic type technique known as manifest typing. For each row value, manifest typing records the values type along with the value data. This allows nearly any statement of any row to hold almost any type of value. In the strictest sense, SQLite supports only 5 concrete data types. These are known as storage classes and represent the different ways SQLite might choose to store the data on disk. Every value has one of these 5 native storage classes. Null. A null is considered its own distinct type. A null type does not hold a value. Literal nulls are represented by the keyword null. Integer. A signed integer number. Integer values are variable length being 1, 2, 3, 4, 5, 6, 4, 6 or bytes, 8 bytes in order, depending on the minimum size required to hold the specific value. Integer have a range of -9. I think it should be 9,223 trillion, 372 billion, 36 million, 854 billion, 854 million, 775,808 to plus, or roughly 19 digits. Literal integers are represented by any bare series of numeric digits without commas that does not include a decimal point or exponent. A floating point number stored as an 8-byte value in the processor's native format for nearly all modern processors. This is an IEEE 754 double precision number. Literal floating point numbers are represented by any bare series of numeric digits that include a decimal point or exponent. Text. A variable length string stored using the database encoding UTF-8, UTF-16BE, or UTF-16LE. Literal text values are represented using character strings in single quotes. Blob. A length of raw bytes copied exactly as provided. Literal blobs are represented as hexadecimal text strings preceded by an X. For example, the notation X1234 ABCD represents a 4-byte blob. Blob stands for binary large object. SQLite text and blob values are always variable length. The maximum size of a text or blob value is limited by a compile time directive. The default limit is exactly 1 billion bytes or slightly less than a full gigabyte. The maximum value for this directive is 2 gigabytes. Since the elements of most columns can hold any value type, the type of a column is somewhat misleading concept. Rather than being an absolute type as in most databases, an SQLite column type as defined in create table becomes more of a suggestion than a hard and fast rule. This is known as a type affinity and essentially represents a desired category of type. Each type affinity has specific rules about what types of values it can store and how different values will be converted when stored in that column. Generally, a type affinity will cause a conversion or migration of types only if it can be done without losing data or precision. Each table column must have one of the 5 type affinities. Text, a column with text affinity that will only store values of type null, text, or blob. If you attempt to store a value with numeric type, that is float or integer, it will be converted into a text representation before being stored as a text value type. Numeric. A column with a numeric affinity will store any of the five types, values with integer and float types, along with null and blob types, are stored without conversion. Anytime a value with a text type is stored, an attempt is made to convert the value to a numeric type, integer or float. Assuming the conversion works, the value is stored in an appropriate numeric type. If the conversion fails, the text value is stored without any type conversion. Integer. A column with an integer affinity works essentially the same as a numeric affinity. The only difference is that any value with a float type that lacks a fractional component would be converted into an integer type. Float. A column with a floating point affinity also works essentially the same as numeric affinity. The only difference is that most values or with integer types are converted into floating point values and stored as a float type. None. A column with a none affinity has no preference over storage class. Each value is stored as the type provided, with no attempt to convert anything. Since type affinities are not part of the SQL standard, SQLite has a series of rules that attempt to map traditional column types to the most logical type affinity. The type affinity of a column is determined by the declared type of the column. According to the following rules, substring matches are case insensitive. If no column type was given, then the column is given the none affinity. If the column type contains the substring int, then the column is given the integer affinity. If the column type contains any of the substrings character, blob or text, then the column is given the text affinity. If the column type contains the substring blob, then the column is given none affinity. If the column type contains any of the substrings like real, flow or dub, then it is given the float affinity. If no match is found, the column is assigned the numeric affinity. As implied by the first rule, the column type is completely optional. SQLite will allow you to create a table by simply naming the column, such as create table T, I, J, K. You will also notice that there isn't a specific list of column types that are recognized. You can use any column type you want, even making up your own names. This might sound a bit fast and loose for a typing system, but it works out quite well by keying off specific substrings rather than trying to define specific types. SQLite is able to handle SQL statements and their database specific types from just about any database, all while doing a pretty good job of mapping the types to an appropriate affinity. About the only type you need to be careful of its floating type. The integer in point will trigger rule 2 before the flow in floating will get to rule 5, and the column affinity will end up being integer. Column constraints. In addition to column names and types, a table definition can also impose constraints on specific columns or sets of columns. A more complete view of the create table command looks something like this. Create table, table name, column type, and column constraints, and then there are table constraints. Here we see that each individual column can have additional optional constraints and modifiers placed on it. Column constraints only affect the column for which they are defined. While table constraints can be used to define a constraint across one or more columns, constraints that involve two or more columns must be defined as table constraints. Column constraints can be used to define a custom sort order like collate, collation name. Collations determine how text values are sorted. In addition to user-defined collations, SQLite includes a no-case collation that ignores case when sorting. A default value can also be assigned. Nearly all columns have a default of null. You can use the default column constraint to set a different default value. The default can either be a literal or an expression. Expressions must be placed in parentheses. To help with date and time defaults, SQLite also includes three special keywords that may be used as a default value: current time, current date, and current timestamp. These will record the UTC time, date, or date and time respectively. When a new row is inserted, see date and time features on page 159 for more information on date and time functions. Column constraints can also impose limits on a column, like denying null or not null, or requiring a unique value for each row unique. Remember that a null is not considered a value, so unique does not imply not null, nor does unique imply only a single null is allowed. If you want to keep null assignments out of a unique column, you need to explicitly mark the column not null. Column values can also be subjected to arbitrary user-defined constraints before they are assigned, like check expressions. Some types of constraints also allow you to specify the action to be taken in situations where when the constraint would be violated. See create table or update in Appendix C for more specific details. When multiple column constraints are used on a single column, the constraints are listed one after another without commas. For example, create table parts, part ID integer primary key, stock integer default 0 not null, description text check description, empty strings are not allowed. In order to enforce a unique column constraint, a unique index will be automatically created over that column. A different index will be created for each column or set of columns marked unique. There is some expense in maintaining an index, so be aware that enforcing a unique column constraint can have performance considerations. Primary keys. In addition to those other constraints, a single column or set of columns can be designated as the primary key. Each table can have only one primary key. Primary keys must be unique, so designing a column as primary key implies the unique constraint as well and will result in an automatic unique index being created. If a column is marked both unique and primary key, only one index will be created. In SQLite, primary key does not imply not null. This is in contradiction to the SQL standard and is considered a bug. But the behavior is so long standing that there are concerns about fixing it and breaking existing applications. As a result, it is always a good idea to explicitly mark at least one column from each primary key as not null. There are also some good design reasons for defining a primary key, which will be discussed in tables and keys on page 87. The only significant concrete thing that comes out of defining primary key is the automatic unique index. There are also some minor syntax shortcuts. If, however, the primary key column has a type that is designated as integer and very specifically integer, then the column becomes the table's root column. SQLite must have some column that can be used to index the best storage for the table. In a sense, that column acts as the master index that is used to store the table itself. Like many other database systems, SQLite will silently create a hidden row ID column. For this purpose, different database systems use different names. So in an effort to maintain compatibility, SQLite will recognize the names row ID, OID, or underscore row ID underscore to reference the root column. Normally, row ID columns are not returned even for column wildcards, nor are their values included in dump files. If a table includes an integer primary key column, then the column becomes an alias for the automatic row ID column. You can still reference the column by any of the row ID names, but you can also reference the column by its real user-defined name. Unlike primary key, by itself, integer primary key column do have an automatic not null constraint associated with them. They are also strictly typed to only accept integer values. There are two significant advantages of integer primary key columns. First, because the column aliases the table's root row ID column, there is no need for a secondary index. The table itself acts as the index, providing efficient lookups without the maintenance cost of external index. Second, the integer primary key columns can automatically provide unique default values. When you insert a row without an explicit value for the row ID or row ID alias function, SQLite will automatically choose a value that is one greater than the largest existing value in the column. This provides an easy means to automatically generate unique keys. If the maximum value is reached, the database will randomly try other values looking for an unused key. Integer primary key columns can optionally be marked as auto increment. In that case, the automatically generated ID values will constantly increase, preventing the reuse of an ID value from a previously deleted row. If the maximum value is reached, insertions with automatic integer primary key values are no longer possible. This is unlikely, however, as the integer primary key type domain is large enough to allow 1000 inserts per second for almost 300 million years, When using either automatic or auto increment values, it is always possible to insert an explicit row ID or row ID alias value. Other than the integer primary key designation, SQLite offers no other type of automatic sequence feature. In addition to a primary key, columns can also be marked as a foreign key. These columns reference rows in another foreign table. Foreign keys can be used to create links between rows in different tables. See tables and keys on page 87 for details. Table constraints. Table definitions can also include table level constraints. In general, table constraints and column constraints work the same way. Table level constraints still operate on individual rows. The main difference is that using the table constraint syntax, you can apply the constraint to a group of columns rather than just a single column. It is perfectly legal to define a table constraint with only one column, effectively defining a column constraint. Multi-column constraints are sometimes known as compound constraints. At the table level, SQLite supports the unique check and primary key constraints. The check constraint is very similar, requiring only an expression, check expressions. Both the unique and primary key constraints, when given as a table constraint, require a list of columns like unique column name, primary key column name. As with column constraints, any table level unique or primary key, which implies unique constraint, will automatically create a unique index over the appropriate columns. Table constraints that are applied to multiple columns use the set of columns as a group. For example, when unique or primary key is applied across more than one column, each individual column is allowed to have duplicate values. The constraint only prevents each individual column to also be unique. You would need to add the appropriate constraints to the individual columns. Consider a table that contains records of all the rooms in a multi-building campus. So create table rooms, and then you have room number, building number, primary key, etc. Clearly, we need to allow for more than one room with number 101. We also need to allow more than one room in building 103. But there should be only one room 101 in building 103. So we apply the constraint across both columns. In this example, we have chosen to make these columns into a compound primary key, since the building number and the room number combine to quintessentially define a specific room. Depending on the design of the rest of the database, it might have been equally valid to define a simple unique constraint across these two columns and designated an arbitrary room ID column as the primary key. Tables from queries. You can also create a table from the output of a query. This is a slightly different create table syntax that creates a new table and preloads it with data all in one command. Create temp table, table name as select query statement. Using this form, you do not designate the number of columns or their names or types. Rather, the query statement is run and the output is used to define the column names and preload the new table with data. With this syntax, there is no way to designate column constraints or modifiers. Any result column that is a direct column reference will inherit the column's affinity, and all columns are given a none affinity. The query statement consists of a select command. More information on select can be found in chapter 5. Tables created in this manner are not dynamically updated. The query command is run only once when the table is created. Once the data is entered into the new table, it remains unaltered until you change it. If you need a table-like object that can dynamically update itself, use a view. A view is in page 43. This example shows the optional temp keyword. The full keyword temporary can also be used in create temp table. This modifier can be used on any variation of create table, but is frequently used in conjunction with the as select variation shown here. Temporary tables have two specific features. First, temporary tables can only be seen by the database connection that created them. This allows the simultaneous reuse of table names without any worry of conflict between different clients. Second, all associated temporary tables are automatically dropped and deleted whenever a database connection is closed. Generally speaking, Create table as select is not the best choice for creating standard tables. If you need to copy data from an old table into a new table, a better choice is to use create table to define an empty table with all the appropriate column modifiers and table constraints. You can then bulk copy all the data into the table using a variation of the insert command that allows you for query statements. See insert in page 46 for more details. Altering tables. SQLite supports a limited version of alter table command. Currently, there are only two operations supported by alter table: add column or rename. The add column variant allows you to add new columns to an existing table. It cannot remove them. New columns are always added to the end of the column list. Several other restrictions apply. If you need to make a more significant change while preserving as much data as possible, you can use the rename variant to rename the existing table, create a new table under the original name, and then copy the data from the old table to the new table. The old table can then be safely dropped. For full details, see alter table in Appendix C. Dropping tables. The create table command is used to create tables and drop table is used to delete them. The drop table command deletes a table and all of the data it contains. The table definition is also removed from the database system catalogs. The drop table command is very simple. The only argument is the name of the table you wish to drop table name. In addition to deleting the table, drop table will also drop any indexes associated with the table. Both automatically created indexes, such as those used to enforce a unique constraint, as well as manually created indexes will be dropped. Virtual tables. Virtual tables can be used to connect any data source to SQLite, including other databases. A virtual table is created with the create virtual table command. Although very similar to create table, there are important differences. For example, virtual tables cannot be made temporary, nor do they allow for an if not exist clause. To drop a virtual table, you use the normal drop table command. For more information on virtual tables, including the full syntax of create virtual table, see chapter 10. Views provide a way to package queries into a predefined object. Once created, views are more or less likely the read-only tables. Just like tables, new views can be marked as temp with the same result. The basic syntax of the create view command is create temporary view name as select query statement. The create view syntax is almost identical to the create table as select command. This is because both commands serve a similar purpose with one important difference. The result of a create table command is a new table that contains a full copy of the data. The select statement is run exactly once and the output of the query is stored in the newly defined table. Once created, the table will hold its own independent copy of the data. A view, on the other hand, is fully dynamic. Every time the view is referenced or queried, the underlying select statement is run to regenerate the view. This means that the data seen in a view automatically updates as the data changes in the underlying tables. In a sense, views are almost like named queries. Views are commonly used in one of two ways. First, they can be used to package up commonly used queries into a more convenient form. This is especially true if the query is complex and prone to error. By creating a view, you can be sure to get the same query each time. Views are also commonly used to create user-friendly versions of standard tables. A common example are tables with date and time records. Normally, any time or date value is recorded in Coordinated Universal Time or UTC. UTC is a more proper format for dates and times because it is unambiguous and time zone independent. Unfortunately, it can also be a bit confusing if you are several time zones away. It is often useful to create a view that mimics the base table but converts all the times and dates from UTC into local time zone. This way, the data in the original tables remains unchanged, but the presentation is in units are more user friendly. Views are dropped with the drop view command, drop view name. Dropping a view will not have any effect on the table it references. Indexes. Indexes or indices are a means to optimize database lookups by pre-sorting and indexing one or more columns of a table. Ideally, this allows specific rows in a table to be found without having to scan every row in the table. In this fashion, indexes can provide a large performance boost to some types of queries. Indexes are not free, however, requiring updates with each modification to a table as well as additional storage additional storage space. There are even some situations when an index will cause a drop in performance. See indexes on page 107 for more information on when it makes sense to use an index. The basic syntax for creating an index specifies the name of the new index as well as the table and column names that are indexed. Indexes are always associated with one and only one table, but they can include one or more columns from the table. Create unique index, index name, on table name, column name. Normally, indexes allow duplicate values. The optional unique keyword indicates that duplicate entries are not allowed, and any attempt to insert or update a table with a non-unique value will cause an error. For unique indexes that references more than one column, all the columns must match for an entry to be considered duplicate. As discussed with create table, null isn't considered a value, so a unique index will not prevent one or more nulls. If you want to prevent nulls, you must indicate not null in the original table definition. Each index tied to a specific table, but they all share a common namespace. Although you can name an index anything you like, it is standard practice to name an index with a standard prefix such as id x and then include the table name and possibly the names of the columns included in the index. For example, create index idx employee name on employee's name. This makes for long index names, but unlike table or view names, you typically only reference an index's name when you create it and you drop it. As with all the drop commands, the drop index command is very simple and requires only the name of the index that is being dropped. Dropping an index will remove the index from the database, but it will leave the associated table intact. As described earlier, the create table command will automatically create unique indexes to enforce a unique or primary key constraint. All automatic indexes will start with an SQLite prefix. Because these indexes are required to enforce the table definition, they cannot be manually dropped with the drop index command. Dropping the automatic indexes will alter the table behavior as defined by the original create table command. Conversely, if you have manually defined a unique index, dropping that index will allow the database to insert or update redundant data. Be careful when auditing indexes and remember that not all indexes are created for performance reasons. Data manipulation language. The data manipulation language is all about getting user data in and out of the database. After all, the data structures and other database objects have been created with DDL commands. DML commands can be used to load those data structures full of useful data. The DML supported by SQLite falls into two basic categories. The first category consists of an update commands, which includes the actual update command as well as insert and delete commands. As you might guess, these commands are used to update or modify, insert and delete the rows of a table. All of these commands alter the stored data in some way. The update commands are the primary means of managing all the data within a database. The second category consists of the query commands, which are used to extract data from the database. Actually, there is only one query command, select. The select command not only prints returned values, but provides a great number of options to combine different tables and rows, otherwise manipulate data before returning the final result. Select is unquestionably the most complex SQL command. It is also arguably the most important SQL command. This chapter will only cover the very basics of select, and then we will spend the next chapter going through all of its parts bit by bit to address the full command syntax in detail. Select goes a whole chapter by itself, chapter 5. Row modification commands. There are three commands used for adding, modifying, and removing data from the database. Insert adds new rows, update modifies existing rows, and delete removes rows. These three commands are used to maintain all of the actual data values within the database. All three update commands operate at a row level, adding, altering, or removing the specified rows. Although all three commands are capable of acting on multiple rows, each command can only directly act upon rows contained within a single table. Insert. The insert command is used to create new rows in the specified table. There are two meaningful versions of the command. The first version uses values close to specify a list of values to insert. Insert into name, table name, column name, values, new value. A table name is provided along with a list of columns and a list of values. Both lists must have the same number of items. A single new row is created and each value is recorded into its respective column. The columns can be listed in any order, just as long as the list of columns and the list of values line up correctly. Any columns that are not listed will receive their default values. Insert into parts, name, stock, status, values, widget 17 in stock. In this example, we attempt to insert a new row into a parts table. Note that the use of single quotes for text literals. Technically, the list of column names is optional. If no explicit list of columns is provided, the insert command will attempt to pair up values with the table's full list of columns. Insert into table name, values, new value, and that's all. The trick with the format is that the number and order of values must exactly match the number and order of columns in the table definition. That means it is impossible to use default values even on integer primary key columns. More often than not, this is not actually desirable. This format is also harder to maintain within application source code since it must be meticulously updated if the table format changes. In general, it is recommended that you always explicitly list out columns in an insert statement. When bulk importing data, it is common to loop over datasets, calling insert over and over. Processing these statements one at a time can be fairly slow since each command will update both the table and any relevant indexes. Then make sure the data is fully written out to physical disk before finally starting out and next insert. This is a fairly lengthy process since it requires physical I/O. To speed up bulk inserts, it is common to wrap groups of 1000 to 10,000 insert statements into a single transaction. Grouping the statements together will substantially increase the overall speed of the inserts by delaying the physical I/O until the end of the transaction. See the transaction control language on page 51 for more information on transactions. Bulk inserts can be sped up by wrapping large groups of insert commands inside a transaction. The second version of insert allows you to define values by using a query statement. This is a very similar to the create table as select command. Although table must already exist, this is only version of insert that can insert more than one row with a single command. Insert into table name, column name, select, query statement. This type of insert is most commonly used to bulk copy data from one table to another. This is a common operation when you need to update the definition of a table, but you don't want to lose all the data that already exists in the database. The old table is renamed, the new table is defined, and the data copied from old table into the new table using an insert into select command. This form of can be used to populate temporary tables or copy data from one attached database to another. As with the values version of insert, the column list technically optional for all the same reasons. It is still recommended that you provide an explicit column list. All versions of the insert command also support an optional conflict resolution clause. This conflict clause determines what should be done if the results of the insert would violate a database constraint. The most common example is insert or replace, which comes into play when the insert would, as executed, cause a unique constraint violation. If the replace conflict resolution is present, any existing row that would cause a unique constraint violation is first deleted. Then the insert is allowed to continue. This specific usage pattern is so common that the whole insert or replace phrase can be replaced by just replace. For example, replace into table name. See insert and update in appendix C for more information on the details of conflict resolution. Yeah, I think that's all for today.